Okay, so we will today try to start some topic. So I am trying something different. So I am writing it on the iPad that I have. So I hope my handwriting will be slightly different compared to what I used to write on a graphic tablet earlier. So today what I will do is I will do something called index notation, or this is also called tensor notation. This is used both in vectors and tensors. Okay. So whatever vector that we know, that is a vector, in what all ways a vector is represented? You may say that a vector is represented by A and an arrow on that. Correct? A vector is represented.
Yes, sir.
Okay, so A with arrow on that. So this is an abstract representation. Now, if you choose a coordinate system, which sometimes we will call it as a basis, then A can be written in terms of components. So let's say A1, E1, plus A2, E2, plus A3, E3. So you may recall that we have some coordinate system represented in this fashion. Okay, so let's say this is x1 axis, x2 axis, x3 axis. And E1 is the unit vector in this direction. E2 is the unit vector in this direction. And E3 is the unit vector in this direction. Then we can write this as a component. So these are called component. These are called components. Components can be written only when you choose a basis. Now, we have three components because we are choosing a three-dimensional space. Three components in 3D space. One can generalize this and you can have n components in n-dimensional space. So in general, a vector can have any number of components depending on the space that you are choosing. Now, in this index notation, represent a vector as a subscript I. This I is called index. Okay, and we in particular call this as free index. Why do we call it free index? Because I or the index I is free to take values from 1 to n in n-dimensional space. So when somebody says that I have AI, this means this represents what is called a vector. Okay, so you have one free index. That means it is free to take values. That means one free index means it represents n values. And that is why it is called a vector. So in an index notation, a vector is always represented as a symbol representing that vector, and then an index, a free index, which is free to take values 1 to n if you have n-dimensional space, or 1, 2, 3 if you have 3-dimensional space. Okay, so this is the concept of free index, and this is very important. Now let us look at another familiar concept in vectors. That is, let A be a vector. So A, B, be two vectors. I am representing in the familiar notation A, B, be two vectors. Then we define A dot B as the scalar product or the dot product of A and B. Okay, so E is a scalar. A dot B is a scalar, correct? If A and B are two vectors, A dot B is a scalar. Now in component form, that means if you would have chosen a basis and you write A as a vector with its components, B as a vector with its components. In components form, how do we write this A dot B? A dot B is equal to A1 B1 plus A2 B2 plus A3 B3. Just like we had written here, that A equal to A1, A2, A3 are components, B equal to B1, B2, B3 are components. Then this is A1, B1, A2, B2, A3. Now in index notation, you write A dot B as AJ BJ. Now this index J is repeated. So we stick on to this convention that repeated indices are summed out. That means this J is equal to 1, J is equal to 2, J is equal to 3, and you have to sum that. That means your AJ, BJ stands for sum over J is equal to 1 to N AJ, BJ. If you have an n-dimensional space, this is what it is. But we don't write this summation. This is understood. Okay. And these repeated indices, like J here, is called dummy index. This is called dummy index because this index will not survive. That means whenever we have a dummy index like this, what is resulting is a scalar. That means it has no index. So I could have actually called this as J or K, it doesn't matter because it's anyway getting summed out. So this index is called summing, dummy index. So we have learned two things. The concept of free index, where the index is free to take values from 1 to whatever is the dimension of the space. And then we have the concept of dummy index, where the index is repeated and summed over. Okay. Now, we can construct quantities like this. From this, what we have learned. So let us say, let's construct a quantity like this. Construct quantity which is called AI Bj. What is this quantity? AI Bj. A is a vector, B is a vector. Because if you look at AI alone, this is a vector. Bj alone, this is a vector. And this is I, this is not, this is J, this is not a repeated index, so we should not sum over. So the first question that I would ask is, for this quantity, how many free indices are there? Number of free indices for this quantity is what? Both are free, right? I is also a free index, J is also a free index. So the number of free indices are 2. That means each index can take, is free to take values from 1 to N, right? So that means I can take value from 1, 2, etc. up to N. And J also can take values 1, 2, etc. up to N. So whatever is this quantity, the number of components, how many number of components will be there for this quantity? N. Not N, because for I can go from 1 to N, J also can go from 1 to N, right?
Yes, 2N, sir.
Is it 2N?
Or N square? I don't know.
So it should be N square, right?
Yes.
Be N square. So if it is 3-dimensional space, you will have 9 components, right? So if it is 3-dimensional space, you can write this as A1, B1, A1, B2, A1, B3, A2, B1, A2, B2, A2, B3, A3, B1, A3, B2, A3, B2. Correct? So this could be 9 elements of this. Correct? So 9
Yes, sir.
or any liquid. Or any liquid. So so what do we call this kind of quantity? It's not a vector.
Tensor.
So this is a tensor. So AI Bj is a tensor. So now we will define the rank of a tensor is equal to number of free indices. The rank of a tensor is equal to number of free indices. So this AI Bj is a tensor of what rank?
2, sir.
Okay. Now we ask a question that if you have a tensor of rank R, let us say. Okay, so let us say that I have a tensor of rank R in n-dimensional space, ND space. That means I'm going to have a T, I call it as a T, let us say. So I1, I2, I3, etc. IR. There are R free indices. So this is a tensor of rank R. So what is the number of components of this tensor? Number of components. Can you figure out what is the number of components of this tensor?
R square.
Why R square?
That is all. The previous example was also like this thing, right? Number of indexes. No,
Yeah. So
I
the
think it's
number of free indices were 2.
yeah. So it will be like R to the power R, something like that.
What, Nancy? What was your answer?
So 3 to the power R.
Why 3?
Sir, in the above case, we have 9 components, that is 3 to the power 2.
Correct. But I did not say it is 3-dimensional space, right? I said it is n-dimensional space.
N to the power R, sir.
So that is equal to n to the power R. See, if you have a third rank tensor in 3 dimensions, you will have what? How many components will be there? 27 components will be there. That is because it is 3 cubed. Right? So similarly, if you have a n-dimensional space and R tensor of rank R, you will have n to the power R components. You follow that?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
The number of components is n to the power R. Okay, so let us now ask a question. So is there some tensor that you are familiar? Okay, so the most familiar second rank tensor. Okay, So give an example. Of second rank ones.
Moment of inertia.
Hmm? Which one?
Kronecker delta.
Huh. So one of the examples is a Kronecker delta. This is a second rank tensor. Is this a second rank tensor or not? There are two free indices, right? Delta ij. This is a second rank tensor. What
Yes,
are
sir.
the components of this in 3 dimension, for example? What are the components of this one? With 1, 0, 0, 0, 1, 0, 0, 0, 1. Correct? When I is equal to j, it is 1, otherwise it is 0.
Yes, sir.
Correct? So this is a very simple example of a second rank tensor. Okay, so what is this called? This is called Kronecker delta. Okay, suppose if I ask you a question, that is, I have AI multiplied by delta ij. What will be the result? How do we do this operation? AI delta ij.
Sir, AJ.
So how is it aj?
So because Kronecker delta will have 1 only when I equals to j.
So the combined operation, see, AI is a rank 1 tensor, right? It's a vector. Delta ij is a rank 2 tensor, right? So now what is the operation? What is the result? Result is a vector or a, what is the rank of the resultant operation?
So rank 1.
It's a rank 1. So here I is repeated. So which is the dummy index and which is the free index?
I is
I is
I is dummy.
dummy.
Correct? I is dummy and j is free. So I is dummy means what? I must sum over I, right?
Yes, sir.
Sum over I. Correct? So that means suppose I fix, let's say fix j. So let me say that this is equal to some bj. Bj is equal to ai delta ij, because the number of free indices should be same on either side of any equation. Okay. So here there is j is free index on the right side, there should be free index j on the left hand side. So it should, I will call it as bj. Now suppose if I fix j, I want to know what is b1. What is b1 equal to? How do I write b1? How do I?
sir A1
A1
del I11 del 11.
L11. I have to sum over I, right?
Yes, sir.
A2,
A2 del 12. So 2 1.
1 plus
Similarly, A3.
3, 1. Correct?
Sir, I have a doubt.
Huh.
Sir, generally rank sometimes called number of independent columns in a matrix. In that sense, I'm just having some confusion how to understand that.
Okay, that is the rank of matrix. Okay, so rank of a tensor and rank of a matrix are two different things.
Okay, sir.
Okay, so rank of a matrix is different. So this
Okay.
rank and that rank are not same.
Okay.
So you notice here that this delta 21, delta 31 are what?
0.
0. Because you see here, delta 21 is this, delta 31 is this. So they are 0. So this is equal to A1. Now you can see if you take B2, then what will you get? B2 is equal to A2, right?
Yes, sir.
And B3 is equal to A3. So that means we get AI delta Ij is equal to simply Aj. So actually it is the same vector, right? AI and Aj are it's the same vector.
Sir, here you got that delta ij and ai. Delta ij is second rank tensor and ai is a vector, isn't it, sir?
Correct.
In this, my question is, this is a vector ai and delta ij. In delta ij there are two indices, and in vector it has got just one index.
Hmm.
So in that case, we can consider a quantity which is like a tensor into vector. The first indices, if they match, can we consider it as repeat indices, sir? Like, can I split it like that? That's what my question is.
Yeah. The repeated index, whether it is there within the same tensor or it is there in, see for example, so I think if I understand your question, suppose if you
Yes,
have
sir.
delta II, what is delta II?
3.
This is 3 because I is repeated. So it is delta 11 plus delta 22 plus delta 33. Each one of them is 1, right? 1 plus 1 is equal to 3. Correct.
Tensor வச்சு கேட்டுட்டு இருக்கோம். ஐனா மைனஸ் அது இல்லடி இது இண்டெக்ஸ்ல வர ஐ.
1 1 2 2 plus 3. We follow?
Yes, sir.
Sir, I think you are muted, sir.
Is it okay? Can you hear me now?
Yeah, yes, sir.
So here what happens, this I belongs to A and this I here belongs to delta H. So what Ritesh is asking is, can we still assume that this repeated index is summed over? Because this is of two different, the answer is yes. Because when we define the dot product, how did we define? AJ, BJ, correct? J becomes, the index is for different symbols, but still if it is repeated, then it will be summed over. So in the same way, here AI delta Ij, I is different, belongs to different symbols, but then it can be summed over. So whenever index is there, same index, you should sum it over.
Yes, sir. Yes, sir. My question was that if it is a vector and vector, it is fine. My question was if it is a vector and tensor, like different.
See,
So yes for that also.
One of the major advantage of this notation is that once you write them as index notation, you should not bother about whether it is a vector or a tensor. Okay, so index notation's advantage is that everything is a tensor. This is first rank tensor, this is second rank tensor. So if there are indices that are same, sum it over. That's all.
Okay, thank you, sir.
Okay, So let us look at a different quantity. So define something like this. We are just playing around. So let's define AI delta JK. What can you say about this animal? How many free indices are there?
Three.
3, sir.
3.
What can you say about this?
Sir, but you have a condition for canonical delta j equal to k, then only we have 1.
Yeah, that's fine.
So the rank is 1
Rank is 1. Why?
for I.
See,
Okay. Okay, sir.
so we have said that the rank is equal to number of free indices, right?
Yes, sir. Yes, sir.
So how many free indices are there?
3.
Should be its rank.
3.
3.
So
Okay.
this should be equal to either AJ or AK.
What? Should be equal to either AJ or AK.
Yes, sir.
Do you agree that it's a tensor of rank 3?
Yes, sir.
Okay. So how many components?
We ha-
If it is 3-dimensional space, how many components will be there?
20
Why 9?
It's 27, sir.
It should be 27, right? 3 cube. Correct. It's a third rank tensor, right? 3 free
Yes, sir. Yes, sir.
Okay. Now, how many non-zero components will be there? That is the question. How many? Can you find out how many components are non-zero?
So 3.
Sir, 6.
3, 6. Why 3?
So when J will be equals to K will equals to I, that will be one non-zero component.
Hmm.
And then when so I equals to J is equals to K, so that should be 3 such numbers.
But why should I be equal to J or K?
So Kronecker data will be non-zero only if J is equals to K, right? So
Agreed.
that is one value.
Agreed. How many such values will be there? See,
So the reverse process also taken.
what I'm saying is, let's say, let me call this as Tijk is equal to AI into delta JK. What does that mean? I can take values 1 to 3. J can take values 1 to 3. K can take values 1 to 3. Agree? I can take values 1 to 3. J can take values.
Yes, sir.
K can take values.
Yes, sir. So 9.
Huh?
So like 9 components.
9 components will be non-zero. So tell me how the 9 components are non-zero.
So using the condition J is equal to K, so 3 components and 3 into I. 3 components.
So for example, I take A1.
Once.
So A1 delta 1 1, that is non-zero. Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
A1 delta 2 2. Is it non-zero?
Yes, sir.
A1 delta 3 3. Is it non-zero?
Yes, sir.
Yes, sir.
Okay. What else?
A2 delta 1 1.
1 1. A
A2 delta 2 2. A2 delta 3 3. A3 delta 1 1. A2 delta 2 2. A3 delta 3 3.
So these are non-zero. All others are zero. So out of 27, 9 components are non-zero. Even though this is a third rank tensor, but most of those things are zeros. Correct?
Yes, sir.
Because it doesn't matter whatever is I. For every I, j equal to k is 1. That means there are 3 such things, and there are 3 into 3, right? So that is how you will get 9 of them. I have listed them here, but so if you have a n-dimensional space, then what will happen?
So what is number of independent or number of non-zero elements?
Total number of elements will be n cube, right?
Yes, sir.
So number of non-zero elements will be
N square.
n square. N square of them will be non-zero. Correct?
Yes, sir.
Okay. Now let's look at an example of a third rank tensor. This the previous one is also a third rank tensor. So this is called Levi-Civita tensor, denoted by epsilon ijk. Okay, how is it defined? So let us define it. Now, if you think of, let's say 1, 2, 3, let's say 3-dimensional space. Now 1, 2, 3 or 2, 3, 1 or 3, 1, 2. These are called cyclic permutations, right? So this will be equal to 1 if this ijk is equal to 1, 2, 3 or 3, 1, 2 or 2, 3, 1. These three are cyclic permutations. Just like I am starting from 1 and going to 2, 3, or start from 2, 3, 1, or start from 3, 1, 2.
Sir, only in one direction, or
Yeah,
we can.
only in clockwise direction. If I go, I will get these 3 values. Okay.
Yes, sir. Yeah.
Now, this is also equal to -1 if this ijk is equal to, there are totally how many permutations of 1, 2, 3 are there? 6 are there, right?
Yes, sir.
Factorial 3. 6 are there. So there are other 3 which are called non-cyclic permutations. That means you can, so you go in the opposite direction. So that is, let's say 1, 3, 2 or 3, 2, 1 or 2, 1, 3. Okay, so go in the clockwise direction. So these are non-cyclic permutations. Now this is equal to 0 if any 2 indices are same. If any two indices are same, then this becomes 0. Okay, so as you can see, the definition, please try to understand this definition. This definition says that it's a third rank tensor. So this is rank 3. So the number of components is equal to 27. Let's consider 3-dimensional space. How many non-zero components?
6.
9. 9.
Zero components are
6.
where are 9? 6 only,
Oh,
right?
oh, yeah. I thought the previous example.
Totally 6. So 21 components are 0. Okay, 21 components are 0. So this is a very useful tensor. Okay, we can do many interesting things in vectors using this. Using this. For example, suppose if I ask, so some we have talked about dot product of a vector, right? But we can also define cross product of a vector. Suppose I have a vector A, and then I have another vector B, and then we ask, what is A cross B? That is, A cross B is a vector, right? So suppose if I say A cross B is equal to some C, it's a vector, then I want to write down what is Ci. In the index notation, C vector is written as Ci, right? I is the free index. So you can see that this is equal to epsilon ijk into aj bk. In the index notation, this is how we write down a cross product. Now let's try to understand this. For that, let's say I is equal to 1. That means I want C1. So that is equal to epsilon 1 jk aj bk. Now j is repeated, k is repeated. Right? So j is dummy and k is also dummy. They have to be summed over. Correct? So that means this is equal to, so how many, if I write down the sum, there will be 9 terms on the left hand side. Correct? There will be 9 terms on the left hand side. But then fortunately, I don't have to write all these 9 terms because of the definition of this epsilon ijk. In those 9 terms, if j and k are repeated, then epsilon becomes 0. Correct? So j and k are not repeated. How many possibilities are there? I is already 1. So jk can be, j and k cannot be 1. Suppose if I fix j to be 2, then k has to be necessarily 3. Correct? So that means epsilon 1, 2, 3, A2, B3. What is the other possibility? Epsilon 1, 3, 2 into A3, B2. Is there any other term? Even though there are 9 terms, but I know because many of these epsilons are 0, only these 2 terms will be there. So what is epsilon 1, 2, 3? Epsilon 1, 2, 3 is plus 1. And epsilon 1, 3 is minus 1. So this is equal to A2, B3 minus A3, B2. So that is your C1. As you can. So how do you write this? You will write it like this, right? So E1, E2, E3, A1, A2, A3, B1, B2, B3. The determinant. This is how you write down your A cross B, right? A cross B is always written like this. So first one is basically the determinant of this submatrix. A2, B3 minus A3, B2. So that is what we have got here. Now you take I is equal to 2, you will get again the relevant. So in general, a cross product can be defined by using this epsilon ij. Now, as you can see that the epsilon ijk is also related to determinant. So suppose I have a matrix. Okay, so let us say that let M be a matrix. Such that Mij is ijth element. Okay. Then one can also write down determinant of M is equal to epsilon ijk into M1I, M2j, and M3k. How many terms will be there? Because ijk are all the three are dummy. So there will be the whole thing will be a scalar. Correct. So for example, let's say that so let us fix I is equal to 1 just to start with. So epsilon 1, 2, 3 into M11, M22, M33 plus epsilon 132, M11, M23, M33. Now this is nothing but this is equal to M11 into M22, M33 minus M23, M3. So this is the first term, right? M11 into this. So if you take I is equal to 2, you will get the other term, and I is equal to 3, you will get the other term. So you can write down the determinant of a matrix in this following fashion. Okay, so it's not very different because this cross product also has a determinant structure. Okay, so this is another use of this epsilon ij.
Sir,
Yeah.
sir, here M23, M32 will be 0 or not?
See, your matrix M is written in this fashion, right? So determinant of M is equal to M11, M12,
Two.
M13, M21, M22, M23,
Okay, sir.
M31, M32, M33, right?
Yes, sir.
So the first term is what? You take this M11,
Yes, sir.
then take the determinant of this, right?
Yes, sir.
M3 minus this.
Okay, sir. Now I understood.
So if you take next term, that is if you take I is equal to 2, for example, then you will get this term into determinant of that submatrix, then this term into determinant of that submatrix. So like that, you will get all the terms.
Sir, in general sense, how do we define a tensor?
Yeah, so tensor is defined by using certain transformation matrices. Okay, so that we will come to, but I'm just trying to give a sense of recognizing it. Okay, so we will formally define using the transformation matrices later. Okay, so I think the question that you're asking is that if you say that I have a bunch of 9 components, can I call that a tensor? You cannot call that a tensor. So even though a second rank tensor can be written like a matrix, but not every matrix is a tensor.
Okay.
Correct? So there are certain transformation properties that this should satisfy to qualify to be a tensor.
Okay.
Okay. So now since that we have okay, so I think we have it's 11:30. Ritish, Professor Kapoor has joined.
Yes, sir.
Okay, so you please then take a look at these definitions. Then we will continue the next class. So we will